Hi everyone. We discuss in this video the topic of bias initialization, which is basically how to initialize the bias units, not the weight parameters. And this is typically a much easier problem than initializing the weights. And the reason is basically twofold. The first part of the reason is that there are far fewer bias units than weight units, right? So there is a bias parameter, than weight parameters. So there is a bias parameter for every unit in the network, but typically there are far more weight parameters. So for example, if I have a layer 10 by 10, right? So 10 units and 10 units, right? And fully connected. So all these are connected. Then there are, so let's say these are 10, these are 10, right? And here you will have 100 weight parameters, right? And 10 plus 10 bias parameters, right? So imagine 100 by 100, not 10 by 10. Then there will be 100 times 100, 10,000 weight parameters, and only 200 bias parameters, right? So typically there are far less bias parameters than weights. So the choice, so optimizing the bias parameters is actually something that should happen in the first few training iterations, and typically these values will stabilize. Now, the second part of the reason of why initializing bias is easier than initializing weights is that it's actually clear how you should initialize bias, right? So, for example, initializing the bias units for the output units, the bias parameters for the output units should be set to be equal to the marginal statistics of the output. So, for example, if I have 10 classes and 10 softmax units corresponding to the 10 classes, I should initialize the bias parameters of these softmax units to the marginal statistics, the probability of observing each of these classes in general, right? So I have a training set consisting of images of humans, cats, and dogs, and so on, and it's an object recognition problem. Each of the class corresponds. First class is the probability of observing a cat. Second class, probability that the image corresponds to a cat. Second class, probability that the image second softmax unit correspond to the probability that the image correspond to a dog, and so on. I should initialize the bias parameters of the softmax units to the marginal probabilities, right? So if I believe that 10% of the images are images of cats, then the bias parameter of the first softmax unit should be 0.1. If I believe that the 50% of the images correspond to humans, then the bias parameter of the softmax unit corresponding to the class of humans should be 0.5, and so on. So this is for the output units. Now for the hidden units, the bias parameters should be initialized to avoid initial saturation. Basically to enable learning to enable that learning is activated in the first few iterations for as many of these units as possible. And saturation means, so remember, saturation means that the sensitivity of the cost function to small changes in parameters is very small. So the bias should set these hidden units in a region where the cost function is sensitive to small changes in these hidden units, right? So for example, if I have a ReLU, I want the bias if the weights are all initialized to small values. So the linear part will have a small value, the summation of the WX, right? So I have here W1 times X1, W2 times X2. Right? If the W's are small, so W1 X1 plus W2 X2 is expected to be small. So I set the bias, let's say the bias here is equal to B, right? I set B to a small positive value. Why? Because I want that small positive value to push the ReLU into the active region, right? Remember, the ReLU is inactive whenever the value is negative. So W1 X1 plus W2 X2 plus B, if it's negative, then it's not active. At the start, I want it to be active. So the W's are small random values, but the B is a small positive value, right? So that you avoid initial saturation of this unit. Now let's say the bias is multiplicative, as in the case of recurrent networks, for example, long short-term memory units. The bias here is multiplicative. Not only that, but it gets raised to a power, right? So you can go easily into saturation if you have a value much greater than 1 or a value much less than 1. Because when it's raised to a power, it vanishes or it explodes, and in both cases, either you get unstable learning or you get a cost that's very insensitive to changes, right? Which is the vanishing gradient. So you set the bias in this case to be close to 1 because you want to enable learning. This is the area where a choice is being made about this unit, right? Another choice for bias parameters is that bias, and it applies also to weight parameters, is that one can use trained parameters in one model to initialize the parameters in another. So a typical strategy is basically to use a simple model and train it first, and then you use the parameters in this model to initialize a more complex model. And one strategy related to this that we will discuss in detail at the end of this section is basically supervised pre-training. And the advantage here is basically it can improve generalization. It's also inspired by nature from the idea of inheritance, basically inheriting genes, right? So you inherit whatever was successful in the previous generations, right? And that becomes your initial point, and then you learn on top of that. The same idea here. You initialize a model, which is the parent, you train a model, which is the parent, and then you obtain the parameters, and you initialize the parameters of the child node with the final parameters of the parent node. Thank you.